All right, so good afternoon to everybody. It is my pleasure to introduce the first speaker for this afternoon, Professor Lei Zhang from University of Florida in Gainesville. Professor Lei was a student of Yang Ali, Rutgers, and he has a very close ties with the math department in Fortaleza, UFC. He has a very nice collaboration with Eduardo Teixeira. So, Lei, it's a great pleasure to have you here, and I hope you are having a good time and enjoying Rio. Thank you very much.
Well, thank you very much for the kind invitation from the organizing committee. It's such a pleasure and honor to come to here to speak for the first time in my life. The conference has been wonderful. Today, I'll mention something that most of you probably are not familiar with. Since the title of the conference is called the trends, current trends of mathematics, probably the organizers will be happy to have one more trend at least. So it will be my joint work talk about my joint work with Changshu Lin from National Taiwan University and Professor Juncheng Wei sitting in the audience. Okay. First, I'll talk about, first, it is a system of elliptic equations. I'm going to mention, if you look at the simplest form, you can see that Laplacian U and then 2, the coefficient is very important. 2, the nonlinearity is exponential. 2 times e to the u1 minus e to the u2, and then the second equation minus e to the u1, and then 2 times e to the u2. And then, so this is a system defined in the second dimensional spaces. Okay. And then it is possible to talk about more general cases, and then I can add the direct masses on the right-hand side. And then the number of equations does not necessarily have to be 2 anymore. Could be, the strength of the direct mass is bigger than -1. For most applications, they are non-negative, but from an analysis point of view, we always want to make it more general than usual. So it is -1. It doesn't mean too much. And then there are I equations, and it is important to have the coefficient system to be like this. So if I extend the equation, the number of equations from 2 to general, then this will be the coefficient matrix. And it's a very special matrix. It's called Cardan matrix. And then you can see that all the entries on the diagonal are equal to 2. And then there are 2 sub-diagonals. All the entries are -1. And then all other entries are all equal to 0. So this is a very special matrix. And then I'm going to talk about something about the system. And then, so for the system, the most interesting case is when you consider when it is defined on the Riemann surface. Riemann surface 2-dimensional, and then we consider no boundary. And then for convenience, we consider volume equal to 1. And the total system of n equations belongs to this form. Here, of course, you see when you if it is on a compact Riemann surface, when you integrate on Laplacian UI, it becomes 0. So that's why you need to have this -1 over there. And then rho I, there's just a positive parameters. And then for equations, for system of equations like this, then it is very easy to verify that for any solution, if I just add each component an arbitrary constant, that wouldn't make any difference. You see, Laplacian UI plus whatever constant is still Laplacian UI, and then e to the UI, if I add a constant, cancels with the constant downstairs. So it is reasonable to consider solutions that belong to such a space. So each component is H1, but the integration is equal to 0. Okay, so when you consider a system on the manifold, this is what happens. Okay, and then such a system is variational. There's a variational form of this type, and then this Aij tells you the entry of the inverse matrix. The Cardan matrix is invertible. Okay, and then if there's only one thing that my talk is interesting, that would be the background. Very rarely I see a system of equations that has so many connections with other fields, except that my education background is not enough to give you a very long introduction of this background. But I assure you that this system of equation is related to algebraic geometry. In fact, let me just mention a few things. If you consider global solutions, for example, I just take global solution as an example. Laplacian ui plus aij e to the uj, say, equals 0. And then aij is this Cardan matrix in R2 with finite energy. Then each global solution can be interpreted as a holomorphic curve from C to Cpn. And then on the other hand, any holomorphic curves by something in algebraic geometry called the Plucker's formula can be interpreted into such a solution. And then let me just mention one thing. There are quite a few instances that the tools from algebraic geometry have been applied to solve PD problems. And also the PD approach are also used to extend our understanding about algebraic geometry. So it is amazing to see the interplay between two fields. And also if the equation, if there's only one equation in the system, and then this is related to a famous Nuremberg problem. In fact, in application of Chen-Simons gauge theory, if you simplify some algebra, letting some parameter tend to infinity, then you also see total system. And then the total system is integrable system. And for the single equation, it was first discovered by Liouville more than 150 years ago. Anyway, there were many motivations, and then the background is there were a lot of literature talking about the different connections between total system and the different fields of mathematics, even different disciplines of sciences. Okay. And then before I talk about the main results that I want to present, let me first consider the single equation. So if I reduce the system into a single equation, and then I'll mention some results. So I just consider Riemann surface. I just assume the volume equal to 1. Doesn't really matter. Then if the system is reduced to a single equation, then this is called mean field equation. That looks like this: Laplacian u plus parameter rho multiplied this. H is a positive smooth function. And then it was proved by Yan Li and Shafir that if rho is not a multiple of 8 pi, then you have an a priori estimate. So let me draw a picture. So starting from 8 pi, 16 pi, and 24 pi. So if you take rho away from a multiple of 8 pi, then all the solutions in that space has a priori estimate. So once you have that, you can rewrite this equation. You can apply Laplacian inverse on both sides. Then you call this operator T rho. And then you write, then solution of that one can be written as a solution I minus T rho. And then because of the a priori estimate, if you take R large enough, then 0 will not touch the boundary of BR. Then therefore, Larry-Shelder degree is defined on each of the intervals over here. And then it turned out that this Larry-Shelder degree only depends on the topological information of the manifold. So, and then it was Changshu Lin and Junquan Chen who derived such a formula. Later, I'll show you the formula. And then in their derivation of this formula, it needs to let me just mention their main ingredient, the main estimates they proved in their papers. So what happens is when you jump from one multiple of 8 pi, one interval to another interval, and then you have to consider what happens, the number of blow-up solutions. In fact, so this is the first estimate that Changshu Lin and Junquan Chen proved that if rho k approach a multiple of 8 pi, and then in fact the m is an integer, so in this case on the manifold there will be exactly m blow-up points, and then rho k will be extremely close to 8 m pi, and the difference between them is very crucial in their approach. And then, so here, sigma k is just integrating, is just some scaling factor. Don't worry about it. And then the leading term, which is crucial, is involved with the h function evaluated at the blow-up point, and also the Gauss curvature at this point. And then there's a sharp error estimate. And then, so let me draw a picture. So for example, on a manifold, if you have two blow-up points, and then there's a sequence of solutions tending to infinity centered around these points. And then in this case, rho will be tending to 16. And the difference between 16 pi, rho and 16 pi, is calculated by an estimate like this. And also, in the second estimate, they prove that the location of blow-up points has to be the derivative of something tending to infinity tending to 0 sufficiently fast. Also, the sigma k, the epsilon k is integrating factor. So here, of course, the expression is long. Let me just mention the nicknames of these two estimates. First is the closeness to parameters. Second is the first degree derivative on the location. Okay, so you hear when you see that in this estimate, it is involved with the first derivative of the Green's function and its regular part, and also the h function. Okay. And then let me show their results. So they proved that if rho is less than 8 pi, the degree is equal to 1. If rho is between two multiples of 8 pi, and then the degree can be computed by the topological information of the manifold. This Euler characteristic is equal to 2 minus 2 genus, which is the number of handles. So this is the this is topological information. So as a consequence, you can see very easily that if the number of handles is at least 1, then this Euler characteristic is non-positive, and then this one is non-zero. When it's non-zero, we know the solution exists. So as a consequence, so if the genus of M is not 0, and then rho is not a multiple of 8 pi M, there is always a solution to the mean field equation that I mentioned before. For example, for manifolds like this and this. This is a remarkable result because this one, the calculation of d rho, the expression of d rho is only involved with topological information. We know that if you stretch the manifold, as long as you don't rip it apart, and then the topological information doesn't change. On the other hand, the way to derive that is involved with very delicate blow-up analysis. And then the calculation of these estimates involved a very precise description of blow-up solutions. And then it is important to capture the term that is involved with the geometry at the blow-up points. Okay. So and then the second motivation, before I mention my result, is that if I consider the system that has 2 equations. So just now I talked about the result that has only 1 equation. And then if I consider the system of 2 equations in this is called SU3 total system. And then the second result I want to mention is a remarkable paper by Changshou Lin, Juncheng Wei, and Zhao, Chunyi Zhao. So they derived some major estimates that are very surprising to me. So they have a major assumption. They just prove that the key estimate is like this. If you have a number of blow-up points on the manifold, okay. For example, you have a few, and then they prove that they make assumption that each blow-up point is a fully blown up point, which means in the neighborhood of each blow-up point, when you rescale according to the maximum of blow-up solutions, and then it converts to a full system, which means no component is lost after in the process of taking limit. So this is a major assumption. And then they proved, so this is the version so they rescale the solutions according to some parameter epsilon k, and then they proved some estimates that first for the system of two equations, each rho 1k must approach a multiple of 8 pi with amazing precision. So we have a leading term, and multiply epsilon k log epsilon k plus a sharp arrow term. And then each component, because right now the system has two equations, rho 1k, rho 2k, they both approach 8m pi. And then this is the first estimate. And then the second estimate, that they have the location of blow-up points. And then here, it's very similar to the result of Chen and Lin for the single equation, except that they have two of these. And then this is involved with the first derivative of h functions, and also the first derivative of the Green's functions. And also, surprisingly, they have another. That is very shocking. Of course, the expression is long, but here, I only want to bring to your attention two things. First, this is involved with a second derivative of h functions and the Green's functions. So the first condition is the closeness between rho k and the multiple of 8 pi. And then the second condition is involved with the derivatives, first derivatives. And then there's a third condition. They proved that there is another condition that has to be proved. Don't worry about these things. These are defined by global solutions. So here, so they have two conditions. Keep in mind that the number 2. And also, it is involved with the second derivatives of h functions. Okay. So this is what they, and also they proved that there's a vanishing rate, O epsilon k to the beta. Beta is number between 0 and 1. So this is the first time I've seen such estimate for a system of equations like this. Okay, so I mentioned, and also I just want to bring, for system of equations, it's very sad fact that there's no symmetry at all. So here I just gave you an expression of global solutions to SU3 systems. So suppose there are only two components in the system, and then the expression is so complicated. As you can see, the number of parameters that it takes to express the two branches are like this. First, you have 2 real numbers. Then you have 3 complex numbers. So altogether, there are 8 parameters to describe 2 global solutions. And then if you look at that, I'm not sure if you want to look at that. It looks so complicated, and there's no symmetry, whatever. So it's not easy to derive estimates like this, even for a system of 2 equations. Okay, then what I want to present, the main results that I want to present today is that together with Professor Lin and Professor Wei, we extended the results for the 2 equations to any number of equations. So under the same assumptions, we assume that if there are blow-up points, then the blow-up points are fully bubbling sequences, which means after scaling, no component is lost. And then, so also we derive 3 types of estimates. First, each component, so there are n such estimates. I goes from 1 to n. Each rho ik is very close to a multiple of 4 pi. And then the difference between rho ik and this can be captured as a sequence. So these ckit, they're a sequence of positive numbers bounded above and below by positive constants. And then we can also capture the geometric information at each blow-up point with the leading term like this and with a sharp error estimate. And k is the Gauss curvature, and then m is the number of blow-up points, and then epsilon k is the scaling factor. So this is the first estimate. And then the second estimate is about the location of blow-up points. And then here, this equation we derived. So there are n such equations, I going from 1 to n, and then gradient 1 means differentiation with respect to first component. And then there's a location of the blow-up points involved with the first derivatives of Green's function and also h. And then the third, of course, this is very graphic. I'm sorry. And then there are 2n minus 2 second order derivatives So also the location of dot points will have to satisfy another 2n minus 2 set of equations. And then it's involved with the second derivative of h, and then the second derivative of h functions. Here, I want to bring your attention to this one. So the second order derivatives conditions, there are 2n minus 2 of them. So here, you don't see this when it comes to a single equation, because when you plug in n equals 1, 2 minus 2 equals 0. So this is the reason why you didn't see this such an estimate in Chen and Lin's paper. And also, if you plug in n equals 1, n equals 2, 2 multiplied by 2 minus 2 is 2. So this is the reason why the paper of Lin, Wei, and Zhao derived two such equations. So this is the general version. And also, if you look at the error term, Lin, Wei, Zhao's estimate was O epsilon k to the beta for some beta between 0 and 1. So for the general case, for the second order derivative, we also improved their estimates.
There's a slight break in symmetry. You chose some coordinates. You have the partial derivatives difference between the first derivative, partial 1, 1, and 2, 2, and then
Right.
the next one you have partial 1, 2. So
Yeah, right.
hyperbolic
Yeah, it is correct.
Yeah, so I mean, is it just that it's just the all linear combinations of those and
Right.
the whole span?
Right.
So you just pick.
Yeah, I'll tell you the reason why these things come up. I'll tell the reason. Okay, I'll mention key ideas of the proof. So all these estimates depend on a very precise description of the blob sequences. So here, if you remember what I mentioned about our assumption about the blob solutions, suppose you have a sequence of blob solutions and then fully bubbling, which means after scaling, they converge to a system of n equations. And then in the neighborhood, for example, you see two branches. And what we need is to describe the behavior of the fully bubbling sequences extremely precisely. But so this one, so I'm going to mention how to obtain such estimates. But however, there are a lot of difficulties. At least such set of problems is very different from all the problems I have seen before of the same nature. First, global solutions, there's no symmetry. Similar estimates are already obtained for equations like Yamabe type equations, and or even for single equation. Usually, what people do is, in order to describe a blow-up sequence very precisely, they want to consider the limiting function. And usually, the function that the limiting function has a lot of symmetry. So what they do is to compare the solution with the limiting function, and then they do a lot of analysis. Many times use Fourier analysis to take out the part that is non-symmetric. And then usually the part that is non-symmetric are very important to carry geometric information. But that approach fails miserably because there's absolutely no symmetry over here. And then the second part, major difficulty, there's no maximum principle whatsoever. If you remember what I mentioned about the Cardan matrix, there are a lot of negative entries. Oh, those negative entries make maximum principle fail so bad. There's basically no chance to do that. And then a third one, abundance parameters. So if I remember what I counted for you, for the global solutions, for the R03 global solutions, it takes 8 parameters to describe 2 components of a solution. In general, if you describe n solutions, it takes n squared plus 2n parameters to express them. And so this looks like a very looks very terrible. Okay? And then usually for such equations, for single equation, positive identity, which is a balancing condition, has proved to be very, very useful for single equations. But here, when it comes to system, there's only one positive identity that is very challenging, is almost useless, very limited. The use is very limited. And also, what comes for system of equations, a partial blow-up phenomenon is a major difficulty. This is the reason why we assume all the blow-up solutions are fully bobbing, which means after scaling, no component is lost after taking the limit. So let me describe to you what is called a partial blown up. So if you have only two components in the blow-up sequence, what happened is, if you want to rescale the system of equations according to the magnitude of the larger one, then after taking the limit, because the difference between the maximum of these two branches is tending to infinity, and then after taking limit, the second component is gone. So this is something called partial blow-up phenomenon. But it doesn't mean that the second component is not important. That this is just not the case. You can have pictures like this. The first component looks large in a small neighborhood, but the influence of the second component could be very, very big, or could be very big later on. And then you can see pictures like this. For pictures like this, if you rescale according to the neighborhood of the maximum of the first component, at the beginning, the second component doesn't look important at all. But the second component may grow up and becomes very influential later. Anyway, so here, the idea of the proof has a lot to do with the classification of global solutions. So let me first mention a result, the simplest case, when you reduce the number of equations to only one equation, then this is a result by Congming Li and Wenxiong Chen many years ago. They proved that if all the solutions satisfying Laplacian u plus e to the u globally with finite energy belong to such a form. So as you can see, there are a lot of symmetry over here. Lambda is a parameter. And then this is x naught is the center of symmetry. And then if lambda is very large, then the energy is very much concentrated into the neighborhood, around the neighborhood of the origin. And then the total integration is just equal to 4. So there's only, even though there's a whole family of functions, but they have only one energy, which is equal to 4. And then all these functions at the behavior of all these functions at infinity is minus 4 log x plus 0.1. And then, by the way, this is a result. This problem was greatly motivated by a famous result by Caffarelli, Gitas, and Sprague for Yamabe equation. As many people know, that result is for equations of this type, Laplacian u plus some constant n minus 2 for convenience. And u to the n plus 2 over n minus 2 equals 0 in Rn. N has to be greater than or equal to 3. And then they prove that all the solutions are symmetric, they belong to one family. So this is a very influential result. I guess many people know this. And then Congming Li and Wenxiong Chen, they use the same approach, method of moving planes, to prove this. And also, if you have a singularity, then you can see that the symmetry is destroyed. Projapad and Tarantello proved all solutions belong to a certain form. And then in this case, if the gamma is an integer, and then it's very likely no symmetry. And then what I want to mention is for total system, any number of equations in a total system, this Aij is the canal matrix. And then if all the singularities are gone, or all the gamma I are equal to 0, I think it was Jürgen Just and Guofeng Wang who proved to give a classification. But for the regular case. And then their description is in the language of algebraic geometry, which I don't want to repeat over here. And also they actually used some classical theorem in algebraic geometry to prove this, and then they have an interpretation of all the solutions in the language of algebraic geometry. Any totally unramified holomorphic phi from C to Cpn satisfying finite energy condition can be compactified to a rational curve. For analysts, this is, I don't know about you, I feel a little disappointed, because I hope to see if you have a classification of solutions, then I hope to see that what is the solution, what does the solution look like, but they didn't do that. So they just gave a expression in algebraic geometry. And then, I want to talk about this wonderful paper, in my opinion, published on Invenzioni in year 2012 by Chang Shoulin, Jun Chengwei, and Dong Ye. So they not only did the classification, they also add one singularity. So if you consider the equation Laplacian UI global solution, Aij e to the uj, so you can add one singularity at the origin and global solutions. And then they classified, with finite energy, they classified all the solutions. Even though the solution looks a little complicated, but I'll just mention to you, first, of course, you need to do a little transformation on the solution, whatever, that's not the point. So they can write the first branch of the solution in this way, and then by polynomial, the polynomial can be written in such a way. And then once you have the first equation, the first component, you can use the first component to write the second component, and so on, to write all n components. But here, because there's a lot of information, I want to organize your thoughts by writing down the number of parameters over here, because I'm going to refer to these ones later in my idea of the proof. So there are a lot of parameters, altogether n squared plus 2n of them. And then first ones, you can see that the lambda 0 to lambda n, they are real numbers. And then the only restriction for them is that their product has to be some specific number. So lambda. OK, so altogether, there's one restriction. So there are n of them. And also, the second part I want to bring to your attention is that there's a CIJs. CIJs, they are complex numbers. So I put them into the form of a matrix. So C0, 1, C0, n minus 1, C0, 0, sorry. C0. And then Cn minus 1, n minus 1. I just put them in such a form. And it's very easy to count that there are since each one has two components. So you have n squared plus n of them, and then plus the n parameters over here. So n, altogether, n squared plus 2n parameters. So it takes this many parameters to write the global solutions. So these three people were able to do this using wonderful ideas from intergroup system. And then here, again, each component, even though there are so many parameters, each component actually only has one energy. It's very interesting. And also, each component at infinity has only one behavior. Okay. And then, not only so, we also, in our proof, we also used very essentially the non-degeneracy of the linearized system. So these three people, Lin, Wei, and Ye, proved that when you consider the linearized system, and then, of course, there are so many parameters, and we all know that for a global solution, if you integrate, if you just differentiate on each parameter, so there are n squared plus 2n of them. So at least you can have n squared plus 2n families of linearized solutions. But that's it. So that's all of them. So they proved that that's all of them. This is very important. So of course, under some mild growth assumption at infinity. So this is the proof is involved, but this is one of the major ingredients in our proof. Oh, and also, of course, I didn't give you a degree counting formula for the system, but I truly think that there's something in the proof that is very surprising. Is very, very new because as I said, we have to defeat all the lack of symmetry. We need to defeat lack of maximum principle. But if there's no symmetry, and then the solution looks horrible in the neighborhood of the blow-up point, then how do you get a point-wise estimate extremely precise and up to a certain order and get the geometric information afterwards? How do you do that? Oh, the fact is, so this iteration, so the approximation of blow-up solutions by global solutions. So we want to show that the blow-up solutions look very, very close like global solutions. But how do we capture the closeness? First, we said so that U can be a fully bubbling solutions near 0. And then here, suppose VK is the rescaled version, and VK converts to a global solution. But vk converges uniformly to v as a global solution. Well, this closeness is nothing. It's nothing. It doesn't serve the purpose. We need very precise estimate up to a certain order. And then what do? The first part of the proof, we actually wrote it in a separate paper because if we put them together, it'll be too long. So we find a sequence of global solutions. And then we know that for the sequence of global solutions, they are, each one of them, each k has a family of n squared plus 2n members to represent them. So we have a whole bunch of, we have n squared plus 2n family of parameters. And then we have to make sure that the parameters don't go away, so they have to converge to this. The way we do that is we match, so this is very new, is we match the first component of uk with vk on n squared plus 2n carefully chosen points. So this one takes a lot of linear algebra. So among all the approaches we have seen in similar problems, they always use symmetry, and they always match all the information at the blow-up point to use the non-degeneracy. But this is, the whole approach completely fails. But here we use a very different idea. So we match just one component of a blob sequence with the first component of the rescaled version of the blob sequence. And then we have to choose these points very carefully to make sure that all the parameter sequences converge to the one that represents the global solution. This is a lot of linear algebra, but it is based on the non-degeneracy of the linearized system. Or the idea behind that is that when we can do that, if we can do that, roughly speaking, the difference between the sequence of global solutions, the first component of the sequence of global solutions, and the first component of the rescaled blob solutions, they are so close, when you take the limit has to converge to 0, roughly speaking. And if the first component goes to 0, then all other components tend to 0 anyway. And then here, let me just describe very briefly. So here, this is the rescaled blow-up sequence that we want to estimate. So this is the global solutions that we want to use to approximate. So our goal is to show that this guy is really, really, really small. And then I just put it in a very lousy way. So when I look at the difference between these two sequence of functions, and then they look like this. So there's the expansion on the right-hand side, and then there's an error term at this moment. And then here, the e to the beside jk comes from mean value theorem. Here, and then the process of doing this is that I want to first prove that these guys are equal to a very, very small of the order O epsilon k. So when these are of the order O epsilon k, there's another epsilon k over here. So this one can be combined into the second term. And then we worry about the second term later. So the whole process is in a iterative manner. So we prove some estimates, we improve the estimate, and then up to the sharp order. And then here, how do we do that? So here I'm just cheating. So I pretend that this hjk is just a constant. I pretend that this guy is just some global solution. And then what I do is I want to choose among the n squared plus 2n families of solutions to the linearized system. So I want to choose very carefully among them, n of them, to multiply to both sides of the equation and integrate the parts. So let me go back to this equation. You can see that the left-hand side, if I pretend that this one is just a global solution, this one is just a constant, and I multiply a solution. So if you only look at this part, this looks like the linearized system. And then when I suppose I can choose I put a global a solution to the linearized system over here, and I do the integration by parts, and then here I replace the unpleasant term by the global solution, then it looks like this. This is very easy verification. Okay, so this is what happens on the left-hand side. On the right-hand side, also, you just do the integration by parts, you can have this. But this already tells you a lot of information. The reason is, I take omega k to be a very large ball of radius epsilon k to the -1. And then, if you do the integration by parts, suddenly, if you look at the left-hand side, you have oversimplified version of some terms, but that's not the point. Suddenly, you push the integration of this guy to the boundary. As I said, all the solutions look horrible. But once you push everything to the boundary, it is not too bad. So here, the motivation of this is I need to worry about, usually when you push to infinity, things become much better because all the unpleasant terms that happen in the neighborhood lead to become much less unpleasant later. So what I need to do is choose good ones. And then this is the right-hand side of the equation. So if I can choose good ones among the linearized solutions of linearized system, I can make this one disappear upon certain order. So I was cheating when I mentioned about the major difficulties that the system of equations represents. One of them I mentioned abundance of parameters. There were n squared plus 2n parameters. Actually, I was taking advantage of this. So there are so many solutions to the linearized system. What I need to do is I choose some of them to serve the purpose to do the integration by parts. So this is something actually I'm taking advantage of, is rather than difficulties, actually a big source of wealth, actually. So if I make a long story short, I'm not sure how much time I have. I have less than 20 minutes. But so roughly speaking, I chose some of them, and then to do the integration by parts, that I can prove that this guy disappears at a certain order, this guy disappears at a certain order. Okay, so this is the main idea. And then so we first prove that the gradient may vanish at a certain order, and then to obtain the second order, we need to choose another 2n minus 2 members among the n squared plus 2n solutions, family of the linearized solutions. And then this is a long story short. And so in order to do that, we need to study these solutions. So this one depends on the work of Lin, Wei, and Ye. So they have already written down what the solutions look like, the n squared plus 2n parameters. So all we have to do is to sit down and look into these solutions. At the beginning, it seems very unpleasant, but you know there's a big wealth of treasure in there, so you can sit down and work out really hard. So it turns out, let me just write down the conclusion. So as I said, for global solutions, if you look at the behavior at infinity, it is possible to write them down. As you can see, that for the m's component, if you write down, there's some unpleasant number, but it's not too bad. If you look at what happens at infinity, you have the leading term. This term, first we have a constant, and then the second term is comes from this guy, m plus 1 minus m, m minus m. If you look at what I wrote over here just now, at least all the n squared plus 2n parameters over here, and then I found that so the second row over here becomes very important. So they contributed to the leading terms of the expansion, and then actually as I said, by differentiating on parameters, I can get the solutions to the linearized systems. So actually, by differentiating on these parameters, I got the set of solutions to the linearized system that proved this vanishing rate. And then if I keep working harder, and then I see that I can get further terms into the expansion of global solutions. And I found that these guys are particularly interesting. So there's a constant term, there's 1 over r term, and there's 1 over r squared term, and there's another term which is useless. And then these terms come from these guys, n minus 2 minus m, n minus m. So which means I found that in order to get the second derivative estimates, so differentiating on these parameters are very useful. If you count the number of entries in this matrix, you will see that there are n conditions and there are 2n minus 2 conditions, 2n conditions, 2n minus 2 conditions in these estimates. So that's roughly the idea. And then the expansion of these solutions really depends on, relies on the paper of Lin, Wei, and Ye. So you just have to be extremely patient and work out a lot of linear algebra to find out all this information. But the important thing is to realize these guys are really important, and these guys can be used to get the desired estimate. Oh, I have about 50 minutes. If you remember what I said, we assume that all the blob solutions are fully bubbling because we need to prove that all the solutions are fully bubbling in order to have a degree counting formula. Here, I just want to mention report to you another system that is very different in nature. I'll mention some different features, and then it's called the Liouville systems. Liouville system, we consider the coefficient matrix to be symmetric, non-negative. So this is the major difference. So each entry is non-negative. So it's called the Liouville system. And then irreducible. Irreducible means we really consider one system. It's not the two subsystems, not related to each other, pretending to be a part of the system. We're not talking about that. So all the conditions are basically very reasonable, and we assume the matrix to be invertible. There are a lot of assumptions, but we just call the assumption H1, and it has a nickname called the standard assumption. So I want to tell you some stories about the Liouville systems that I worked with Professor Changshou Lin. And then I want to mention two things. First, classification result about all the global solutions. Second, degree counting formula. So first, when you consider global solutions of the Liouville systems under these assumptions, so to make a long story short, it is possible to classify all the solutions. Just the description of the classification theorem takes a little effort. So if you consider the total integration, the energy, I call this energy of each component, I call it the sigma I. And then actually the total integration of these guys will determine the long behavior of each component at infinity. And there's a theorem by Chipard, Ida Shaffier, and Wolanski. Is that you? Oh, it's not you. Okay. So they prove that all the solutions are radial with respect to a common point. So for Liouville system, there are a lot of symmetry. And then the energy vector, they have to satisfy one requirement. This is complicated. So first, all of them, they need to belong to a curve, hypersurface, minus one dimensional hypersurface. But if you take only a part of the indices, and then there must be an inequality. Let me just give you a picture so you all know what I mean. So if I take a system of two equations, and then do you see the red part? So roughly speaking, that sigma and sigma 2 tells you sigma and sigma 2 represent the energy of two components. So they first have to belong to a certain curve. And the second, they can only become part of the curve, which is the red part within the square. So all the global solutions have to belong to a certain part of the curve. And then they also, and then they prove this. They also prove that if you take any point on the red part, there's a global solution. But they didn't prove uniqueness. You need to prove existence and uniqueness. And the uniqueness was completed by myself and Professor Changshou Lin. So we proved, so once we prove the uniqueness, we have a classification theorem. So we prove that if you rescale the function appropriately, and then these two functions, they both satisfy the same Liouville system with the same energy. And then, of course, so we prove that if you have UV being solutions with the same energy, the only difference between them is the scaling. So we completed the classification theorem for Liouville system. And then we move on to consider the system of Liouville equations defined on Riemann surface. And we proved, so this was the H1 assumption that we made. And then in addition, we have to assume something very technical. So we have to make assumption on the inverse matrix. Then inverse matrix, on the inverse matrix, each inverse matrix and each entry on the diagonal has to be non-positive. But each entry off the diagonal has to be non-negative. And when you take the sum of each row, has to be non-negative. We call this, the nickname is a strong interaction assumption. Why does it have to be, why is it called a strong interaction? Because the nature of this assumption basically says the ties between the different branches of the system is very strong. Let me give you some example. When you consider a 2x2 matrix, this is an if and only if condition. So you need to have each Aij non-negative, but the maximum of these two diagonal entries is less than A12. A12 tells you the part that's shared by the two components. So A12 has to be large enough in order to satisfy this condition. So A12 tells you the interaction between two conditions. And then if you have 3x3 matrix, this is the example that how H2 is satisfied. So if you put the zeros in the diagonal and then three other places, A1, A2, A3, then A1, A2, A3, they are positive. They satisfy any two of them. The sum of any two of them is bigger than the third one. Then such a matrix. And then these A1, A2, A3, they indicate the ties between the different components of the system. So under this assumption, we prove the degree counting theorem, so which is this. So we first identify curves. So there are some critical curves that the parameters rho satisfy. And then we derived a priori estimate for regions enclosed by these curves. Sometimes these regions are not even enclosed. And then we proved the degree counting each one of them. So in each such region, there's a well-defined degree counting formula. And then we derived the degree counting formula like this. That only depends on the topological information of the manifold. And then finally, so of course, as a consequence, as a consequence, if the Euler characteristic number is non-positive, we can prove the existence of a solution. Just recently, I emailed to Professor Lin. Professor Lin told me by email that he has found this unreasonable assumption. He said, he told me that he has seen such matrices in number theory. So it's very surprising. We have to assume this in order to rule out very unpleasant situations. But actually, it turned out that he asked someone to teach him number theory, and then suddenly this matrix came out. So sometimes it's very amazing to see the ties between different fields very unexpectedly. Thank you very much for your attention. It's not easy to listen to my talk.